everyone, and welcome to our webinar today, Accelerating AI from the Cloud to the Edge. Our presenter today is Wei Li, and Wei is Vice President and General Manager of Machine Learning and Translation at Intel Corporation. Fascinated by cutting-edge technologies throughout his career, he led his teams to innovate and achieve significant product impact on Intel business from data center to cloud, mobile devices, CPU co-design to artificial intelligence. He was an adjunct professor at Stanford University. He has a PhD in computer science from Cornell University and is a graduate of the Executive Accelerator program from the Stanford Graduate School of Business. He served as an associate editor for ACM Transactions on programming languages and systems. And throughout his presentation, please feel free to send any questions you may have. We have another one of our experts in the background who will be answering any of your questions as they come in. And if we have some time at the end, Wei will also take a few of your questions live. So with that, we will turn the time over to Wei.
Thank you, Mike. Hi, everyone. Welcome to this seminar. And I understand there are 1,500 people signed up for the seminar, so it's a great opportunity to speak to all of you, but it's also a challenge for me to speak to a wide audience. So my goal is I want to give you a pretty comprehensive presentation of Intel AI, and so hopefully each one of you can get something out of it. The goal today is to cover Intel from both hardware and software perspective to accelerate AI from the cloud all the way to the edge. Let me try to move the slide here. Okay, good. Now, all of you are on the internet pretty much almost every day, right? Every day, 7 days a week, 24 hours a day. And a lot of us are generating quite a bit of data traffic. So studies show that an average user like us would generate 1.5 gigabytes of data traffic each day by 2020. And that seems to be a lot of data. Now, in comparison, there will be much, much more data generated by the machines, the things that are connected to the internet. So if you look at something like autonomous driving vehicle, it will generate somewhere around 4,000 gigabytes a day. And if you look at smart factory, it will generate even more, something like 1 million gigabytes. So it's actually 1 petabyte. I had to actually look at the word petabyte a while back. So the numbers are really, really growing fast. So what do we do with all that data? When you look at compute side, the computation also involved quickly in the past many years here. So years ago, I used to work with a database vendor in the Bay Area. So actually, we have engineers sitting there working with them side by side to optimize their databases. Because at that time, when you had a lot of data, usually you put in a table, in a relational table. And for example, in a meeting like this, we will have a database, record of 1,500 people with your name, your affiliation, and all that. And we can do something like a SQL query to find out, who you are, who are you with, and all the good information from there. So the goal was to speed up the processing of that kind of transactions as quickly as possible. At that time, when we worked with that database vendor, we were able to set a world record on TPCC. For those of you who are familiar with the transactional database side, also we set a record on 64 nodes, a cluster of 64 nodes. So at that time, it was considered a supercomputer, was very, very significant. Now, fast forward to today, I have a team actually, as we speak, working on machine learning training in the cloud. So the cloud has a lot more compute power over there. So our goal is trying to experiment with maybe 1,000 nodes, and that's equivalent of 100,000 vCPUs if you're buying compute from the cloud service providers. So things have changed. The amount of compute has changed. The amount of work has changed as well. And the other thing that has changed is there's so much research in the area of AI. And I'm actually speaking to you from LA, where I'm attending the NIPS conference. And there's a lot of research going on. People are presenting papers. There are a lot of posters here. There are a lot of companies setting a booth here. There's a lot of activities going on here. So the innovation is actually moving very quickly here. Because of all these three reasons, AI has become a very big opportunity for all of us here. And the estimate is the AI compute cycle will grow by 12x by 2020. So it's going to be a significant growth. This is going to be another the next big wave for all of us here. Now, what can AI do for us? AI is going to transform everything around us. It's going to be transform every aspect of our lives here. It will impact from consumer side to government, all the way to education and all kinds of things you can imagine. A couple of months ago, I went to Stanford Medical School because I'm based in Bay Area. So I went to Stanford Medical School and attended one of these meetings over there, and I saw that the AI-based software can actually read X-ray in a much better in a better accuracy than radiologists. So in that sense, AI has arrived for that particular field. I also have a team working on mobile devices. So as part of that, we develop software and hardware. Intel is doing both hardware and software for it, and we need to do validation. So initially, when we did that, we actually hired contractors to do this, and that's a very interesting job where you will be sitting all day there, playing games and get paid for it. When I first mentioned this to my children, they actually all like it. They all want to apply for that job because they can have some fun and getting paid for it. But then this is also a very boring job because we actually had somebody who joined us the first day and quit immediately because it's hard to play the same game again and again. And from our perspective, it is very expensive and also very slow. So what our team did was we actually developed a robot using artificial intelligence, and that robot can detect more bugs than human testers. So that's another application where AI actually has already impacted our current work here. Now, how does AI work? The AI has been around for many years. When Turing started the field around 1950, so it's been more than 60 years. And AI went through ups and downs. Initially, it was a big hype, as we are going through today also. And then AI went through a long winter. Only recently, AI has come back simply because of a sub-area inside AI called deep learning. So deep learning is a special subfield inside the area called machine learning. And for deep learning, usually you have the goal here is to train a particular model. So for example, in this particular case, you have a model here which will take an image, for example, a picture here, and the model will tell you whether something is a person or something is a animal here, right? So the goal is to be able to do detection. And if you're doing self-driving car, you have a sensor, you have a camera, you want to be able to detect if the person is walking by or if it's just a road in front of you. So there's a lot of image recognition you can do using AI as the example here. Now, machine learning has two phases here. The first step is to do training. That's where you build this particular model. And the second phase is when you have the model, you deploy in different places. During training, usually it will take some training data and then have the machine train the particular model so that eventually you get the right accuracy. Now, deep learning is also based on a particular mathematical model which use something like neural networks. And I have a picture here, and a neural network is a simple structure where you have multiple layers, and each layer has multiple nodes. And think about the entire network as a particular function. So you have the input out to that function is going to be all these images, and the output of the function can be something like a classification where you can tell whether something is a person or not. So during training, you will feed the data to this model, and then over time, the model will train and get to the right accuracy. As you can tell, because it takes a lot of data to train the model, so training may take a long time. So sometimes hours, sometimes days, sometimes weeks. And usually training requires so much computation, it's done in the data center. Once you have a model, you can deploy the model. So when you use the model, it's called inference. So when you feed the model with a picture, the model is supposed to tell you whether the picture is 97% chance of person here, or it is 97% chance of something else. And on the inference side, it can usually be done on the edge. For example, you may have a camera. You want to have inference done on the edge, or you may have something in the data center where you actually feed your information back to the data center, and it will do the data center training from there. So it could be done on both sides. Now, in either case, you want to make sure the response time is fast. Because people interact with the applications cannot wait for a long time to do this. So on the training side, from compute perspective, it is usually a lot of computation is more throughput oriented because you have a lot of data coming in. On the inference side, it tends to be more latency oriented where you want to get the work done as quickly as possible. So how do we support something like AI from the technology perspective? So Intel is a hardware company. We also do software inside, and we are really a systems company where we want to make the building blocks to support something like AI. So from that perspective, we need to make sure we have actually both opportunities and challenges on both sides from the hardware side as well as the software side. So what I will be talking to you about is both hardware and software. And inside that, what you want to cover is from the cloud all the way to the edge. So there are a lot of opportunities on the cloud side as well as a lot of opportunities on the edge side. And there are many players going into this on NIPS today. Yesterday I went to they have a show going on here where they have a lot of companies doing demos, and from the big companies like Intel, Facebook, Google, to quite a few small startups, where the small startups are doing something like hardware accelerator only for deep learning, as well as a small software startup where they actually do something like automatic hyperparameter tuning. So there's really a lot of opportunities for many people here. So let me show you how Intel is doing, what Intel is doing on the AI side. Let's look at the hardware side first. So the Intel approach on the hardware side is we have what we call portfolio approach, and we have quite a few different hardware offerings here, and we cover different usages and the different scenarios where you want to have different kind of hardware for that. And we have certain hardware where we actually can, you can do it for both the training side and the inference side. For example, Intel Xeon CPU, you can use for both training and inference. And there are certain hardware we actually targeting a particular usage. For example, we have the Intel NERVANA neural network processors. That's an ASIC, which was designed for training only. And on the inference side, we also have something like Movidius VPU, which is designed for computer vision only, and Intel GNA, which is designed for speech only. So I won't have a chance to talk to you about all of these, I'll give you a few examples of what Intel hardware is. Then we can move down to the software side. So let's look at Xeon. And many of you are very much familiar with Xeon. So when you have a data center, you have a Xeon. And Intel Xeon is powering a vast majority of the data centers around the world here, data centers and cloud around the world here. And it is it's a chip and it can run any applications. It can, because particularly if you are a CSP, if you're a cloud service provider, you're doing a public cloud, you have all kinds of customers, and you really have no idea what kind of applications your customers will run on your public cloud. And a machine like Xeon is very much capable of handling all kinds of workloads here. Now, on top of this, we have made a significant progress on Xeon supporting AI, particularly supporting deep learning. So Xeon has been supporting the traditional AI very well for a long time, but on the deep learning side, it's more bigger change recently. And in the Skylake, what we call the scalable processor, which was announced a few months ago, we have made a tremendous performance change for AI. So I'll show you the combined hardware software improvement a little bit later. But the net result is, if you tried Xeon a few years ago, it was taking a long time to do. Now it's going to be very fast. If it took weeks to do a few years ago, right now it will only take a few hours when you do deep learning training here. So the change is very significant. I will also share with you quite a few use cases where we use Xeon to do both deep learning training and deep learning inference. Now, if you really want to do deep learning training only, and if you don't care about other workloads, and you may want to consider accelerators. And Intel is working on a new accelerator called Intel NERVANA neural network processor. And this is actually a very exciting ASIC for us, and it was designed by a company called NERVANA, which Intel acquired last year. This one was designed for deep learning only. And what's interesting was actually last night, so I'm at NIPS right now, last night we had a Intel party actually. During the Intel party last night, if you can see the picture, I don't know if you can see clearly because it's very small down on the right bottom here. These are the co-founders of NERVANA, and they're all part of Intel right now. And they actually, for the first time, revealed the NERVANA chip at the NIPS conference. And this is truly a very exciting moment, not only for the people working on this, but also for Intel as well. And I've been working with them very closely, and it's very exciting to see the new group of people coming to Intel. They're very smart, and in my career, I have met with a lot of smart people. Quite often, these are the ones with PhDs in computer science. But this time around, a lot of these people have PhDs in neurosciences, and they're very different. And they not only have PhDs in neurosciences, they also worked on chip design before, or they worked on Wall Street as a trader, and really they have a very different background than a lot of us here. Now the chip itself is very unique. It's very different from the CPUs or GPUs, and it is really designed for deep learning only. And as a result, you can imagine you can simplify. You don't need to do all kinds of stuff that a CPU or GPU had to do. So you only need to focus on deep learning itself, and it really means you do a lot of matrix multiplication and addition very well. And as a result, you can increase your compute density, and you can squeeze in a lot of compute power in that chip. And it also has a design where you actually have two different pipelines, one for compute and one for data. As many of you who optimize these workloads before, you know you actually want to have the data ready when you do computation. So because you have two separate pipelines, you can always increase efficiency that way. Now, deep learning training is also very data intensive, and so this also has on-chip memory, very high bandwidth, as well as low latency, and also has the super fast interconnect where you can connect multiple of these ASICs together to do large-scale training as well. So this is going to be very interesting ASIC only designed for deep learning training. Now, in addition to deep learning training, sometimes people focus on deep learning inference. For example, in this particular case, Microsoft is doing deep learning inference in their data center, and we actually have the FPGA, which is well suited for deep learning inference here. So they recently adopted the Intel Stratix 10 as part of their BRAINWAVE project. And there are quite a few advantages for doing FPGA here. One is you can have a very efficient performance per power, because we can do very low power using FPGA here. And the other advantage will be you can customize it, because that's the whole point of doing FPGA here. And particularly when you have something like deep learning, you may not necessarily know what kind of precision you're going to get. You using FPGA, you can try different kinds of precisions only for the particular inference engine you may have. And also, deep learning is a very fast-moving area. When you do all kinds of research, you may also want to, adopt your latest research and reprogram your FPGA. So therefore, you can get the research result quickly to production as well using FPGA. Now, what if you want to do something on the edge? It's good to have inference on the data center side, but the data center usually is a little bit far away from the device you may have, and so you want to do something on the edge side as well. And about a month or two ago, Google announced a new smart camera called Clips, as I show here on the slide. And this is a camera where you can clip on any objects at your home, and it's smart enough to recognize faces. And for example, if your grandma comes for a visit, you can actually track her and automatically take pictures of her. And it's smart enough not to take picture of any random people here. Inside the camera, there's an AI engine involved in image recognition and all that. And it actually uses Intel's Movidius chip. And our Movidius chip is a chip, as I mentioned, designed for computer vision only. And it really has very, very low power. And they're talking about the power envelope of 1 watt, which is very different from a chip that would be used in the data center, usually in the range of hundreds of watts here. Now, in addition to hardware, you also need to look at software. Makes a huge difference for deep learning and AI in general. And at Intel, the advantage is we have a large company. We have both hardware and software teams. And our strategy is we take a very holistic approach for doing this, which means we're combining both hardware and the software. And our software strategy is usually can look at from the 4 different aspects of our software strategy here. And first, we actually work with communities very closely. For example, the developer community, the open source community, as well as the research community. And a couple of months ago, I actually went to a research retreat with Stanford, where they they have a project they are funded by Intel and a few other companies where they try to make AI usable by a broad set of people. We also work with other companies to help them develop solutions. And for example, you can work with some bank to do fraud detection, and you work with, we also do optimizations with application vendors, ISVs, as well as OS vendors like Linux, Windows, and so on. And in addition to that, Intel actually is a developer ourselves. We actually develop software ourselves, and we develop things like compilers, performance analysis tools for developers to use so they can increase the productivity and performance when they develop software here. Now, on top of this, we are more than just a software team here. We actually work with the hardware team very closely. And that's the advantage of in the same company we have both hardware team and software team, and we innovate the hardware features together between software team and hardware teams here. I actually have a team called pre-enabling. So we work with the CPU architects to evaluate various different features, and we do performance analysis of the new ideas. We tell them what features is best for the next generation of CPUs, and then people can make decisions with a more data-driven approach. On top of the performance analysis kind of work, we also develop various kinds of software tools. For example, we do simulators. We do both the application level simulators as well as the platform level simulators for both the functional simulator as well as fast performance simulator. So we do all kinds of simulation infrastructure for the hardware design team as well. Let's see. Okay. Our developer program is very large, and it's one of the top developer programs in the world, actually. And particularly for AI, we have something called NERVANA AI Academy, where we have multiple things going on here. So first, we do training of developers. We will hold all kinds of workshops and seminars like what I'm doing today, webinars, and we also have the tools available on our website so people can download from the Intel website. And I mentioned community already, and most recently, about 2 months ago, we actually announced something called Intel NERVANA Dev Cloud. It is a cloud where we can have the particular academics, the researchers can get access to the cloud to try out their new machine learning models and all that. Okay. Now let's look at the software in AI software side. So Intel is supporting the entire software stack for AI. At the lowest level, you have all these libraries, and we go from we support Python. We have our own Python distribution as well as supporting the main Python branch. And we have a library called DAL, D-A-A-L, which is designed for the traditional machine learning primitives. And we have the NERVANA Graph, which is designed to support multiple frameworks and multiple hardware targets. And we have the math kernel library called MKL-DNN. So all these libraries will actually make use of the hardware features. So they are the ones closest to the hardware interface. And then on top of that, we use these libraries to optimize for the frameworks. As you know, on the machine learning, on the deep learning side, these are the standard frameworks. These are popular. We just dynamically adjust our strategies, priorities. We will support the most popular frameworks out there. So you probably can see TensorFlow, MXNet, Caffe. These are the top ones. And the Neon, the one second to the left, from the left, is a framework that came with the NERVANA acquisition. So it's the Intel's own framework. We We are doing a lot of experimentation on the framework to try new ideas, to push the boundary of performance. And then to the left of that, we have something called BIGDL. So for those of you who follow big data, Spark has been very popular for big data, and that's where data is. And Intel came up with a new framework called BIGDL, which is designed for big data itself. So you don't have to copy your data out of the database, the Spark you already have. You can do deep learning right on top of this. This is very convenient for people who are already on Spark. Then on top of this, we have all kinds of tools. We have the cloud management tool, as well as the BIGDL Studio to help you develop your model. We have the CVSDK for vision, and for many other things here. So let me also give you a few examples of this instead of giving you it will take quite a few hours to cover everything here. Let's see. Okay, so one example here is how do we optimize these frameworks? As I mentioned, we're optimizing all these top popular frameworks here. So our strategy here is we optimize these frameworks built on top of two libraries here. One is the MKL-DNN, the other is ML-SL. When you think about optimizing deep learning frameworks, when you go down from there, it all comes down to a lot of mathematical linear algebra routines. And the good thing is Intel has been in this area for probably more than 20 years, because this is really what the people in HPC work on. And I actually worked on supercomputer more than 20 years ago myself, and we're very familiar with the kind of linear algebra performance optimization you need to do to get the best linear algebra primitives from it. So Intel has been in HPC for a long time, and even as today, Intel processors have been powering majority, I think the last time I saw the data was more than 90% of the supercomputers on the top 500 list, where the two supercomputing community is tracking the latest, greatest supercomputers with that particular list. And every Intel platform has the MKL library on it, and the MKL library is the Intel Math kernel library, which has all the linear algebra routines. So we started from there instead of from scratch to support deep learning. So we have come up with a library called Intel MKL for deep neural networks, MKL-DNN, and this is a open source library, and this is the one we leveraged what we have done inside MKL and added new primitives like convolutions and so on. These are the ones heavily used by the latest deep learning models here. Now, similarly, on the communication side, we have the machine learning scaling library, and Intel is being has a very well optimized a library for MPI, which is the one of the standard message passing interfaces for HPC. So we start from there also, and we built a layer specific design for deep learning, and that layer is called ML-SL. So because of these two, we're able to optimize our frameworks for both single node as well as scaling out for multi-node. So let me show you some performance data in the next few slides here. The first one is on the single node side. And as I mentioned a little bit earlier during the Xeon slide, the performance gain has been very significant on CPU. And that's because we have done both hardware and software optimizations on top of CPU. And if you look at both inference and training results, both of these have improved by more than 100x, simply because the optimization we have done through the library, through the optimizations inside the framework, as well as the hardware itself, has a very significant performance improvement in the latest hardware versus a generation or two before that. So really we have hit a home run here with a lot of performance gain on all kinds of fronts here. Now on the multi-node side, not only single node, we also scale out to multiple nodes here. And this is an example where a research center called Surfsera in Europe, in the Netherlands, they used our software, Intel Optimized Cafe, as well as MLSL. They came up with creative ideas to do training for ResNet 50, and they managed to scale all the way to 500 Xeon nodes. And they set a new record at that time for 44 minutes, which is actually, it's a very amazing result, because before that, something like ResNet 50 would take days to run on all kinds of platforms. And the picture here is a supercomputing center in Spain, and I was always amazed to see a supercomputing center was housed in such a nice building here. It looks like a museum here. Now, this was a few months ago. Now, most recently, I think that was 2 weeks ago, UC Berkeley published new results, and they actually even went further in terms of scaling. So they actually used another supercomputing center in Texas, in UT Austin, and pushed all the way to 1,600 nodes. And as a result, the ResNet 50 time to train got reduced to only 31 minutes, and the AlexNet time to train got reduced to 11 minutes. So the race really is on between multiple groups, and they all try to reduce the training time that used to be days, weeks, and to something. Initially, I actually met with a professor from UC Berkeley last week. We had a meeting at Intel, and he was telling us initially their goal was to finish training during lunchtime, and then they find out they can actually finish training during a break, even less than during a coffee break, even less than the lunchtime here. So it's 11 minutes. I guess that's shorter than a typical coffee break here. And if you do about an hour, it's more like a lunchtime here. So it is amazing to see the training can be done from overnight, from days, to something like hours on minutes. Now, I already mentioned BIGDL, and BIGDL on Spark, where we use the existing data inside Spark, where you can do deep learning directly. And the big data Spark is also designed for not only for tolerance, but also very scalable. And as a result, the BIGDL is also very scalable here. And you can see the scaling from a single node to multiple nodes. The number is probably too small for you to see here, but it's also scaling very well on something like Spark here. So what can we so we have all kinds of hardware. Talk about hardware, different options we have. We talk about software. We build the entire software stack, and we talk about optimizations where we generate a huge performance gain. And so what does that mean for real-world applications? So the next few slides, I want to share with you what we have been able to do for real-world applications here. So first is a few months ago, a company, actually Honeywell, came to us. They wanted to develop a drone to handle high-risk jobs. For example, you want to send a drone to check something like the highway bridge to see whether there's any cracks or not. And you want to send a drone to somewhere where you can see, maybe somebody's building a solar farm to generate electricity, and it's not easy to send people to inspect whether the solar farm is in good shape or not. You want to send a drone to circle around to tell you what's going on here. And you may want to send a drone to check out whether your power line is down or whether the exterior of an airplane is in good shape or not. So there are many different high-risk jobs where you don't want to send people, you just want to send drones there. So they came to us, and we actually, our team, my team developed the machine learning model for them, and where we got the data from, we work with them, they provided data, we provide the model, and the training to do something like a drone only took 6 hours on the latest Xeon processor here. And this is very different from if you try something on Xeon maybe before, it may take many weeks to finish. Right now you can actually do this in a few hours. And this is very amazing to see. For a real world application like this, you can actually use a single node Xeon to get the training done. And this is interesting because I live in the Bay Area, and a few months ago we have the big fire going on, and I wish they can deploy the drones over there. Actually, well, as we speak, I'm in Southern California now, and we actually have a wildfire not far away from LA. So these things can really help making a difference in the real world here. Now, the second thing we did was on drug discovery. As you know, this is another area which is very interesting, and that can have a huge potential to solve our problems here. And in this particular case, we in order to get the best accuracy, because for something like drug discovery, you don't want to live with a very low accuracy. For something else, maybe a reasonable accuracy is good enough. It doesn't do any harm when you're not as accurate. We're missing a few percent here, a few percent there. And for the drug, you really want to be as high accuracy as possible. And in order to do this, they were using. So this is the work with Kyoto University. They have a medical center over there. So in order to get high accuracy, they actually had to use a lot of data samples. In this particular case, they're using millions of data samples there, and that easily required a lot of memory, and more than 100 gigabytes of memory required for doing training there. And this is only available on the CPU, on the Xeon CPU here. And this is not something usually a accelerator can handle. So in this case, we were able to get to very high accuracy using a lot of data, and the part of the reason was we have the optimized Tiano framework. In this particular case, we're using the Intel optimized Tiano framework. In the last drone case, we were using the Intel optimized Café framework. So we are being Café framework. We're being optimizing quite a few of these frameworks here. The next example is using inference. So once you have trained, you want to do deep learning inference. And this is another interesting example where they do the inference inside Amazon Cloud, and they're doing very online, very artistic rendering here. And this was demoed in many different presentations before, where you can take two pictures. For example, you take the Mona Lisa picture on the left-hand side and another Picasso picture on the right-hand side. You can have some creative way of merging these two pictures, and it becomes something very interesting on the left-hand side here, the big picture, which is a merge of these two pictures here. So you could potentially try to submit your picture, your personal picture, and the Picasso picture to see how that looks like. Many people try that already, actually. So this can be done in a very efficient way, because on Amazon you can get cheaper cycles for CPU than other alternatives. All right. Now, in the Bay Area, it is a huge hot housing market, and Many of us have to, if you want to buy a house, you have to actually bid for it. You have to give your bid well above the asking price, and this is really crazy here. And in the way we do it here is you actually, when you buy a home, you actually have something called MSL listing, where you can, it's a database of houses available in the market, where you can search for your dream house here. And this data itself is already in Spark. So it's a very natural fit for us to use BIGDL to do deep learning training and inference on Spark. And in this particular example is if you find a house you like, for example, the house in front of us on the left-hand side, and then this website will tell you other similar properties you may like as well. So this is another example using AI to find similar things from what you like here. Okay, so now we have talked about how you want to use it. Now I know in such a large audience here, we may have quite a few hardcore techies. We want to know how you actually optimize all these software routines and frameworks to get performance to become useful here. So in the next few slides, what I want to share with you is how we actually do the optimizations here. Now, if you think about optimizing libraries and frameworks using the hardware features, you're really talking about doing it's more of a distributed computing here. We want to optimize a large-scale application or system, software system, really using a lot of distributed computing techniques here. So if you think at the higher level, you want to scale out to as many nodes as possible, and that means all the techniques for distributed computing will be very critical here. You want to look at load balancing, and for different nodes, you want to look at reducing the amount of synchronization overhead, and sometimes you want to overlap communications and computation, and all these techniques we have been exploring in the distributed computing community for many years will all come in handy here. And now, when you come down into a single node, nowadays each node has multiple cores in it also. So, for example, a latest Xeon will have more than 50 cores in it. So it's really each node is really looking like a supercomputer in the past. And inside the node, you also want to do parallelization. You want to make sure you do load balancing. So similar ideas will be applied here. And oftentimes in the node, you may have shared memory. So your optimization may be slightly different within the node versus across multiple nodes here. Now for each core, when you dig deeper inside each core, and you may have different kinds of function units over there. For example, you may have on the Intel case, we have a very powerful vector processing units, and you want to make sure you vectorize well on these units here. Now, the last but not least, actually that's probably one of the most important things, is in addition to computation, you also want to make sure you manage your data well, and usually you have a memory hierarchy. They have different trade-offs, and the layer closer to you usually is smaller, but it's much faster. So you want to manage data well, so you can always use the data from your closest to you as much as possible. And we have all kinds of techniques to do blocking for memory, for cache, and so these are the techniques you need as well to make this happen. So there's 4 really categories of optimizations you have to do here. Now let me look at one example here. So this is an example using MKL-DNN, and in a very naive implementation of the convolution algorithm, which is heavily used in deep learning. The naive version is not very friendly to the underlying architecture. So therefore, you have to apply the techniques I mentioned in the previous slide to optimize this. So in this case, you want the latest Intel Xeon processor has something called AVX512, where you can do vector processing on long vectors of 512 bits. It is very a lot of compute that you can do in a single vector here. And you also want to handle data. You want to do data reuse, and then you want to explore multiple cores here. You want to do parallelization. And so the trick here, if you look at the picture on the right-hand side here, is the deep learning has all kinds. You have weights coming in. You have the weights you will need to update, and then you have the input data, and they all come down to matrix operations between these various different tensors here. You want to really make sure you select the right dimensions of these tensors so you can effectively use the vector processing capabilities as well as the multi-core capability as well as the memory hierarchy side. So this is how we end up doing to get the best performance on the library side. And we have something very similar. So if you think about inside the framework, as much as possible, we want to call these libraries. But outside libraries, you also have other routines over there. You want to apply similar techniques over there, and to make sure you optimize well over there. Okay. Now, so this is a single node side. On the multi-node side, we want to look at the entire thing from distributed computing perspective. You want to distribute the software implementation, and you want to make sure you increase your scaling efficiency in some way. And initially, it was actually not easy. About a year ago, it was not easy to scale out to multiple, many different nodes here, because there are really two ways of doing distributed computing for deep learning. One is you want to look at data parallelism. The other is you want to look at model level parallelism. And usually, the data level parallelism is much easier to do. So you just have different data with the same model. You want to run different things there. You want to run the same model on different data here. Now, the data level parallelism is limited by the mini-batch size, because you want to split the mini-batch into multiple nodes. If the mini-batch was small to begin with, it is much harder to do distribution that way. And most recently, there is a breakthrough actually on what we call large mini-batch size. And Intel has somebody working on research on this, and working with Northwestern University. Actually, the professor was there last week. Also, he actually won the von Neumann Theory Award actually recently. It was a very amazing result. And then Facebook came up with a breakthrough on a different way, on a new way of doing large mini batch size. And as a result, right now it opened up so many opportunities to distribute to as many nodes as you want. Because right now you're looking at mini batch size of something like 16,000, which was not imaginable about a year ago. So the field is really moving very quickly. And now, in addition to have a large mini batch size, you also want to, for example, reduce the synchronization costs. So there's a research on different ways of doing that as well. So let me show you the next slide, which is a collaboration between Intel and Stanford and NERSC, and where they came up with a hybrid approach. The traditional way of doing machine learning training is you actually go through one pass. At the end of the pass, you do synchronization. Everybody will wait. You will pass your update to everyone. You synchronize that way. Everybody wait over there, right? That's a bottleneck. So what you want to do is you want to break the synchronization into asynchronous process, where people don't have to wait for each other for getting the latest data. Now you also, but on the other hand, you still need to think in some way. So the hybrid approach is you divide the nodes into multiple groups, and within each group you do the synchronized fashion. You have everybody wait, and then across different groups you do the asynchronous version for this. So because of that, the team was able to scale all the way to 9,600 nodes on a particular workload from NERSC. It's a weather forecast workload from NERSC, and they reached 15 petaflops, and that was really amazing amount of compute they have done over there. And it's also used Intel optimized Caffe and ML-SL here. Okay, so now on the inference side, how do you do optimizations? And usually in this field, usually what people use to do machine learning, deep learning modeling is using something called floating point 32, which is a 32-bit floating point for data format. And on the inference side, people want to see, can they use even less precision? For example, if you use 8-bit, integer 8-bit, which is only 1/4 of FP32, you can reduce the amount of memory, you can reduce some computation. So everything will be good if you can use small amount of lower precision here. And so Intel Xeon actually does support something called INT8, and it does require software enabling to make this happen here. So inside our framework, we managed to use INT8 to achieve, so you can do quantization. You can reduce your model from your training could be done in FP32, and you can use the quantization approach to reduce that to INT8, and you can do INT8 to inference. And as a result, you can actually do it in a very consistent way. You don't really lose much of precision, and you get better performance without losing the accuracy here. Okay. All right. So to summarize, I have give you. Let me just skip this slide here. Oops. Something wrong with the slide here. Okay. So this should go to. Okay. All right. Here we go. So to summarize, I've covered Intel's activities on both hardware and software to accelerate AI from the cloud all the way to the edge. And I know a lot of you guys are interested in AI, and hopefully a lot of you are developers Intel is working with. And together, we will unleash the next big wave, and we will make a difference together here. Thank you all, and I'm open to questions.
Well, it looks like Daniel's got a lot of the questions. Let's see, there are a couple that are left. What do you think about using FPGA on the edge device? In our research, we confirmed Intel FPGA shows very good performance with binary CNN.
Yeah, so FPGA on the edge is actually very interesting. I think it's another place. FPGA can be used on both the data center side and edge side. And I showed example on the data center side where Microsoft used over there, and Intel is working with different groups to look at using FPGA on the edge. And actually, most recently, I ran into a startup doing autonomous driving. They want to use Intel FPGA over there as well. So there's many opportunities for using FPGA on the edge side.
Okay, great. Well, thank you, Wei, for the presentation. We are at the top of the hour, and I know a few other questions have come in, and I will get those in front of Dan, who's been answering questions in the background, as well as Wei, and hopefully we'll be able to get you, email you some answers. So again, thank you everyone for joining us. Appreciate it, and we hope you will be able to take advantage of what Intel is doing in the artificial intelligence area. Have a good day, everyone.
Okay, thank you all.